Hello, 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 and welcome to this week's episode of the Science Show with Dr Dada on Jambo Radio, Scotland, broadcasting from the city of Glasgow. As usual, today we'll be exploring science and technology, and we'll be focusing on the implications these developments have for our everyday lives. And so, you're welcome. This show is going to be very interesting today. It's a very timely topic we have. Today we know it's quite cold. It's been cold for a few days here in Glasgow, and everybody's thinking about heating their homes and various ways in which to do that. And that's why today's show will be having an interesting topic: heat pumps for cleaner and cheaper energy. So in today's episode, we'll be exploring the various ways in which heat pumps can be used as a source of clean and renewable energy. And we'll be discussing how heat pumps work, the different types of heat pumps, and the benefits and drawbacks of using heat pumps as a source of heat energy. So please do sit back and relax, and let's dive into the world of clean energy through heat pumps. And that's why the question of the week is, which is better, heat pumps or gas boilers? So there's going to be a little bit of a wrestling match between the two today. And to facilitate that discussion, we have in the studio an expert in this topic. And we'll be introducing our expert a little bit later. But I am your host, Dr Adetunmise Dada, and this is the Science Show on Jambo Radio Scotland, broadcasting live from the city of Glasgow. And we are proudly sponsored by the Institute of Physics Scotland through the Public Engagement Grant. And don't forget, you can listen to the show on DAB, and you can listen and watch us live at jamboradio.co.uk. And of course, we invite you to follow the Jambo Radio Scotland channel on YouTube for access to episodes and updates on this show. So, what are we going to be covering today then? As usual, we'll be starting with the science news highlights, and we'll be having an interview with our guest. And our guest today is a professor of thermal energy, so he'll be explaining it all to us when it comes to gas boilers versus heat pumps, which is the topic of our discussion. And of course, we'll be opening the lines. We'll be receiving calls from listeners and viewers. What do you think about the future of clean energy? And any other comment, any other way in which you want to contribute to the discussion, that will be welcome. Near the end of the show, we'll be enjoying some science jokes, and we'll be vibing and rapping to a beat. Yay, that will be fun. Let's see how that goes today. So do stay tuned and do not touch that dial. And let's begin. So before we start with the news highlight, we're going to have a quick introduction of our guest. So today in the studio we have with us Professor Zhibin Yu. I hope I'm saying your name correctly.
Yes, a very nice pronunciation.
Yes, thank you. And he is the inventor of the flexible heat pump cycle. And this device enables the development of the next generation of heat pumps, which offer better energy efficiency and flexibility. And his research has attracted wide media attention. So it's really, really great to have you in the studio with us today.
Thank you very much, and good afternoon, everyone. And thanks for having me today. Thank you.
Great. Really good. So could you help us? I know your name is Chinese, and happen to be a student of Chinese myself. So I just want to get the right pronunciation. So how do you pronounce the last name, Yu?
If you want to pronounce my name in a real Chinese way, it will be Zhibin Yu.
Zhibin Yu.
Yeah.
Wow, I've not heard that last name before.
Yeah.
So Zhibin Yu. Okay, Yu.
Yeah.
Professor Yu.
Yes, that's correct.
Good. I'll try to keep that. But if I don't manage it sometimes, please forgive me. So, very good. So, let's get on then into our science news highlights. Today we have only a couple of headlines, and you'll understand why in a moment. The first highlight today is our own news on this show. So the Science Show on Jambo Radio is awarded the Public Engagement Grant by the Institute of Physics, IOP, Scotland. Yay! That's really good news. That means we'll be able to bring to you more science-filled content. And of course, as you know, on this show, we don't only share some scientific facts with you, we also make science fun. So this is really good news. And the second item, the second highlight we're going to be looking at today is something that's been all over the news. In fact, this news just broke yesterday and is really timely because it's also on the theme of energy, of clean energy. And it says, breakthrough in nuclear fusion energy announced. And this is from the BBC. Yay! That's fantastic. I remember many years ago watching films about this, films in which the protagonist basically discovers or successfully performs an experiment in which nuclear fusion worked. So this is a very, very big day for science. And the report just says, a major breakthrough has been announced by US scientists in the race to recreate nuclear fusion. Now, physicists have pursued the technology for decades as it promises a potential source of near limitless clean energy. On Tuesday, which is yesterday, researchers confirmed they have overcome a major barrier, producing more energy from a fusion experiment that was put in. But experts say there's still some way to go before fusion powers homes. The experiment took place at the National Ignition Facility at the Lawrence Livermore National Laboratory, LLNL, in California. LLNL Director Dr. Kim Bodil said, "This is a historic achievement. Over the past 60 years, thousands of people have contributed to this endeavor, and it took real vision to get us here." So you could be asking, well, what is nuclear fusion? As you can see in the picture there, nuclear fusion is described as the holy grail of energy production. It is the process that powers the sun and other stars. So basically what happens, what it needs is it takes two atoms or pairs of lighter atoms and forces them together. And by doing so, they combine to form heavier atoms. And this fusion releases a lot of energy. Of course, the energy comes from the difference in the initial mass of the participating atoms and the mass of the produced atom. So for example, if hydrogen atoms are heated and forced together, combined together, the fusion reaction will create helium and a neutron will be released, as well as a huge amount of energy, going with the E is equal to mc squared equation. Now, nuclear fusion is the opposite of nuclear fission, where heavy atoms are split apart, and fission is the technology that's currently used to power nuclear reactors and nuclear stations. But this process, the fission process, also produces a lot of waste that continues to give out radiation for a long time, and this can be dangerous and must be stored safely. However, nuclear fusion produces far more energy and only small amounts of short-lived radioactive waste. And importantly, the process produces no greenhouse gas emissions and therefore does not contribute to climate change. But one of the challenges is that forcing and keeping the elements together in fusion requires very high temperatures and pressures. So until now, no experiment has managed to produce more energy than the amount put in to make it work. So this is really, really amazing news, isn't it? And the other question to ask is, well, how much does this cost? How much does the facility cost, and how does it work? Well, the National Ignition Facility in California itself is a $3.5 billion experiment, and that's about 2.85 billion pounds. So how does it work? Well, it puts a tiny amount of hydrogen into a capsule the size of a peppercorn, and then a powerful 192 beam laser is used to heat and compress the hydrogen fuel. Now this laser is so strong that it can heat the capsule to about 100 million degrees Celsius. That's even hard to imagine. That's so hot. It's actually hotter than the center of the sun, and it compresses the atoms to more than 100 billion times that of the pressure of the atmosphere. So this is immense temperatures and pressures. And under these forces, well, the capsule begins to implode on itself, and this forces the hydrogen atoms to fuse and release the energy in the fusion reaction. Now, in this particular experiment that we're talking about, the question then is, how much energy was produced? Well, on announcing the breakthrough, Dr. Marvin Adams, the Deputy Administrator for Defense Programs at the U.S. National Nuclear Security Administration, said that the laboratory's lasers had input 2.05 megajoules of energy to the target, which had then produced 3.15 megajoules of fusion energy output. Now, the experiment was only able to produce enough energy to boil about 15 to 20 kettles, and it required billions of dollars of investment. So it doesn't sound like a lot of value for money yet. But of course, with more work, this kind of opens the way for clean energy in future. Fantastic. So that's the end of our news highlights. Nuclear fusion. We'll be having a professor of nuclear physics on the show in the weeks to come. So we'll be hearing more about exactly the physics behind all that in future. But for now, we're going to be going back to our professor in the studio today, Professor Yu. It's really, really great to have you, Professor Yu, in the studio. And today we'll just like to get to know you a little bit more. So, as I said earlier, Professor Yu is currently a professor at the University of Glasgow in the James Watt School of Engineering, and he's a professor of thermal energy. He joined the school in September 2012 as a lecturer and was promoted to senior lecturer in 2017, and then to full professor in 2019. So, really fantastic track record there. But we'd like to know more about you. Would you like to share with us, please, some things about your background, your educational background, as well as personal background?
Thank you very much, Dr. Dada. Thanks for having me today. And so, as you just very nicely mentioned, so I'm a professor of thermal energy. So I work on technologies for heating and cooling our houses and industrial processes. So particularly, I work on the heat pumps and the refrigeration and district heating networks, and this kind of technology we can use to heat our houses, to keep us warm, and to make the energy for the industrial processes. And so these are the technologies I work on. And so it's quite relevant to what we just discussed today, is about how to have a clean energy for future. And so these are the technologies I work on.
That's fantastic. Thank you very much for sharing that with us. And what moved you to pursue this line of research?
Yeah, I think the main headlines nowadays, I think we all know the climate change. So if we remember last year, we had this COP26 in Glasgow. So the main topic was about climate change and how to mitigate the risks of climate change. So we need to keep the temperature increase below 1.5 degrees, in relation to before Industrial Revolution. And so in order to do that, we need to decarbonize our economy and around the world. And in order to do that, we need to, for example, take a UK as the example. So the government made a commitment to reach the net zero target of greenhouse gas emissions by 2050. And in order to achieve this target, we have to decarbonize our economy. This devolved government and the Scottish government had an even more ambitious target, and we are going to reach the net zero target of greenhouse gas emissions by 2045. That is about 5 years earlier than this UK central government target. So obviously this is a big challenge for all of us, for the whole country, for everyone, basically. And so if we look at this target and look at our energy consumption, so actually about half of the energy consumption, and actually is for heating purpose.
Wow.
Yeah, does this include in industrial processes? We need heating for producing steam. We need drying products. We need to melting products, and so on and so forth. And another major application for heating is our houses. Everyone needs a central heating system to keep us warm in winter, particularly like today we got minus 10 degrees. So these are the areas. So we got half of our energy consumed by customers actually for heating purposes. If we want to decarbonize our economy, and obviously we have to decarbonize our heating sector, and this remains a big challenge, right? And if you look at the carbon emissions from our heating sectors, and if we look at the UK as an example, about 37% of the carbon emissions are actually produced by heating technologies or by heating applications. So for that reason, if we want to maintain a target of 1.5 degrees, we need to reach net zero, and we need to decarbonize our economy. And one of the challenges actually is the heating sector. We got to decarbonize our heating sectors.
Yes, absolutely. And we're going to hear more about that when we discuss, obviously, on the different options for heating our homes and so on. But if we come back to you a little bit, then would you like to share with us where you had your initial sort of early education, where you had your early life, and how you got into science?
Well, that's a very interesting question. I was born, south part of China. When I was a child, I was really interested in all kinds of engines, machines,
Wow.
pumps. All these things are so fascinating to me. So when I grew up and I went to university, and I decided to do engineering, and that time actually I did a degree for refrigeration and cryogenic engineering.
Wow. Okay.
So how does this technology work? So basically, it's to find ways to produce cooling. And so, for example, like we need air conditioning. So that is a cooling cell about 10 degrees. In summer, you keep the house cool.
Yes.
And you also need like cooling for keep your food. For example, that is our fridge.
Yep.
And say we need to keep our food about below, 4 degrees Celsius. And if we go down a little bit more, we want to freeze in our meat. So we need a freezer that's say minus 20 degrees Celsius ish. And how about if you go even further down to the temperature, so that we come to something called a cryogenic.
Yes.
So very low temperature technologies to produce cooling effects at a very low temperature for industrial applications, for scientific research, so on and so forth. So that was actually my kind of educational background, and that actually nicely brought me the attention to the decarbonizing of heat. So how are we going to develop novel technologies, innovations, and to help us to reduce the carbon emissions from heating sectors, and how to reduce people's energy bill, for example. So that is really, my research education and my training, and brought me to this very exciting and challenging area for heating technologies.
Fantastic. Yeah, thank you very much for sharing that with us. So, of course, we're going to learn a lot about heat pumps in this show today, and when we come back from this music break, we're going to be asking Professor Yu more about that. But in the meantime, enjoy this song entitled Kilele, and we'll be right back.
What is this?
Nice. That was Kilele by Tana Musica. And Kilele actually means, what is this? And that's exactly what we'll be asking our professor about heat pumps. What's this? What are heat pumps? We'll be learning that in a few minutes. But to start with, we'd like to know a little bit more about your career trajectory, specifically your PhD studies. Would you like to share with us what that involved?
Oh, that's interesting. So after I got my first degree, obviously, how to use power or electricity to produce cooling, and then I changed my kind of direction of my research. When I did my PhD, I actually work on some technology called an engine, and this engine is very interesting. It basically uses the heat and to produce sound.
Wow.
So we call it...
That's nice.
Yeah, so we call it a thermoacoustic engine. So how does it work? So we have a piece of porous material, and we heat one end up to a few hundred degrees Celsius, and then we keep the other end of this piece of porous material to the ambient temperature. And we put this in a pipe, a loop, for example, or a linear pipe. And once temperature difference reaches some threshold value, the sound automatically, spontaneously is generated.
I see.
And so basically you kind of find a way to convert heat energy into a form of power, because acoustic wave is basically a mechanic form of work. It's a power.
Yeah. So
that was the technology called thermoacoustic engines. So I spent about 5 years to work on this technology, and I had a lot of fun.
Yeah.
So after that, that was, I think it was 2005 and 6, and then I had my PhD degree, and then I moved to the University of Manchester as a postdoctoral research. So I then continued to work on this very interesting area for another 5 years.
I see.
And then I moved with the group to the University of Leicester for 1 year. So I enjoyed a lot of research on this very interesting topic. And in 2012, as Dr. Dada just mentioned, and I had an opportunity to move to the University of Glasgow to take a lectureship in energy engineering. And at that time, we start to talk about net zero, we start to talk about decarbonization, and then I see my background and I see my interests, and then I found actually there's a nice marriage between them.
Yes.
So I want to do something interesting and innovative to help people, to help all of us, and to achieve a net zero and to protect our planet.
That's amazing. That's fantastic. Thanks very much for that. And the engines that you were talking about earlier, what kind of sound do they produce?
Well, that's very loud. Very, very loud.
Is it the kind of sound you could make flip into a beat?
You can, because it basically is the frequency. It's
audible.
It's audible. It's actually defined by the length of the system. If you have a longer system, you have a lower frequency. And if you have a smaller system, obviously the frequency will be higher. And one of the things was I'm one of the loudest researchers in the group because it's so loud. So we had a lot of fun to use to either use heat to produce very loud sounds, and then we can use this sound actually to do the reverse effect, actually produce cooling effect and a heat pump effect. So this is why I'm so interested in developing heat pump technologies. You just use different kind of mechanisms, different science, and then you develop different type of heat pumps, refrigerators, and then to produce useful effects.
That's fantastic. Honestly, I need to take this offline. I need to get some samples of the sound that it produces and see if we can make some music out of that as well. Very good. So now we've come to our discussion of the question for the week, which is better, heat pumps or gas boilers? So we're going to have a chat on that, and we welcome your calls as well. So if you would like to phone in live to just ask a question or to contribute to the discussion, you can call us on 0743 782 6865, and that's 0743 782 6865. So now we've come to the question now. First of all, what is a heat pump?
Oh, that's a nice question. So heat pump, And actually, it's more or less the same thing as the fridge or freezer in our kitchen, and it works the exact same principle. So take a fridge as an example. We consume electricity, and we remove heat from the food or drink stored in the food compartments, and we then reject this heat in the kitchen. So you actually use electricity to produce useful cooling effect,
Yes.
and to preserve our food. And if you think we can design a system using exactly the same simple, now we instead of take heat from our food, we actually take heat from a source outside our house. Let's say air, ambient air, or soil, or actually water in a lake or in a river or even in the sea. And then we consume a little bit electricity, and we increase its temperature, and then we send this heat to our central heating system and to our hot water tank. So that actually turns it into a heat pump. So you consume, say, 1 unit of electricity, and you can absorb 2 or 3 units of heat from air or from soil or from river water. And then we actually produce about 3 to 4 units of heat and for our houses.
I see.
Yeah, so this is why heat pumps is an amazing technology. It is very efficient because it only consumes 1 unit of electricity but produce 3 to 4 units of heat, useful heat for keeping us warm or produce hot water for us.
That's nice. That's that sounds really, really good. And thanks for sharing that with us. Not only what a heat pump is and a little bit about how it works. And we have a picture here showing on the screen for those watching. It says, next generation heat pump could cut energy bills and carbon emissions. So this was pulled from one of the news coverages of your work. And there it shows a picture of the heat pump. It looks quite big, I have to say. Of course, this is a kind of prototype, right? So what would it look like in terms of the form factor when it's been maybe deployed into homes or as deployed as a replacement for gas boilers?
Oh, so this picture you have seen and I'll show on the screen actually is a prototype for our invention called the flexible heat pump technology.
Fantastic.
And it doesn't only have the heat pump; it also has an environment chamber at the left corner. So basically, that is actually a chamber we use it to simulate the environment. So it looks like you have a heat pump with a small house here.
Yes.
So in practice, so in reality, actually heat pumps are very compact. It's not much more bigger than a boiler. So it normally come with 2 units. So you got the outdoor unit. So basically, there is a device and basically extract heat from air or from water, and then you actually have an indoor unit.
Yep.
That indoor unit basically is a similar size or even smaller, and that is basically that you transfer heat to your central heating system, like our radiators and our hot water tank.
I see.
Yeah. So in reality, the size of a heat pump is quite compact, actually.
That's fantastic. That's even another advantage, isn't it, compared to maybe gas boilers? Would you say?
Gas boiler, I would say the indoor unit wouldn't. It would be similar to the kind of gas boiler size. Yeah.
Okay.
Yeah. But gas boiler, you only got 1 unit in indoor. So when you come back, obviously you ask me a question of what is the advantage of a heat pump in comparison with gas boilers. I think I'd like to take this opportunity to talk about a little bit more about that.
Yes, we will. And so just before that, a couple of more questions about heat pumps. So can it be used in any climate?
Yes, of course. Actually, this is the amazing thing for heat pumps, because heat pump, as I said, it works on exactly the same principle as refrigeration system, like fridge or freezer or air conditioning. So if you have a heat pump in your house, literally it can produce heating for your house in winter, but it also can be used to produce cooling in summer. And so this is a very common practice in hot climate countries. They have an air conditioning system.
Yes.
So this system can be reversed. So in summer, it extract heat from your house and then reject it
Yes.
outside your house. But in winter, you can change the direction. So you extract heat from outdoor air and then actually produce heat indoor. So
Yes.
so initially in future, I think their systems will help us, to meet the demand for both heating and cooling. Use a single unit, a single system.
That's fantastic. Now, I think let's get more now into the advantages of heat pumps compared with other conventional kind of heating methods like gas boilers and so on. So would you like to start us off? Of course, that will lead us into your invention, where you'll kind of explain that a little bit more to us. So what are the advantages, would you say, compared to gas boilers, for example?
Yeah, there are quite a few advantages when you consider future heating technologies when you use a heat pump. So the first thing is we look at the gas boilers. So the gas boiler, there are kind of two types of gas boilers. We could condensing boiler or non-condensing boiler. So for condensing boilers, roughly give us the efficiency about 90%. You burn, say, 100 units of gas, you produce 90 units of heat. And then when you have a non-condensing boiler, so you actually have an efficiency about, say, up to 78% for in most cases.
Yes.
And so
Wow.
so these are the kind of energy efficiency for gas boilers. But this is only one side of the story. The other side of the story is the gas boilers will produce carbon emissions. We call it the carbon dioxide. Take an average gas boiler, for example, for our household. On average, each gas boiler produces about 2.2 tons of CO2 per year. So that's roughly is equivalent to you take 7 flights between London and New York. So that is roughly your impact to the environment when we use gas boilers every year.
Wow.
Yeah, so that's two things. So in terms of the energy efficiency and in terms of the carbon emissions, so gas boiler has their kind of characteristics. But when you come to a heat pump, so heat pump actually doesn't use gas. It's use electricity, and use electricity to extract heat from a source is free, like air outside, or soil in your garden, or water in the nearby river. And then you use this electricity to drive a device called a compressor to increase its temperature and to a usable level. And then you transfer this heat to your central heating system and to your hot water tank, for example. And that means we can consume 1 kilowatt, for example, of electricity. We can extract 2 or 3 units of heat from the cold air outside, for example. And then we actually produce 3 to 4 units of heat, kilowatt hour of heat, and then for our central heating system. So that means the efficiency for this is actually 300 to 400% if you use the efficiency term.
Wow.
But we use a word called coefficient of performance, and that roughly gave us, say, 3 to 4. That means you produce 3 to 4 times of heat when you consume 1 unit of electricity.
Wow.
So obviously it's a very efficient technology. And also think about the carbon emissions, because we don't consume natural gas to drive our heat pumps. We use electricity.
Yes.
And we got a lot of renewable electricity, particularly in Scotland. We got a huge amount of wind power.
Yes.
And if we think, at the moment we get, in the UK we have about 40% of electricity is generated from renewable sources. And the rest are generated from nuclear power plant and the gas power plant. But in the future, the plan is to generate most of the electricity from fossil fuel based technologies like nuclear power plants, like fusion you just mentioned.
Yes.
And also from wind power, from tide energy, from solar energy. So this kind of renewable power will decarbonize our grid. So it means if we have renewable electricity and we use renewable electricity to generate to drive our heat pumps, it means we don't have any carbon emissions from our heat pumps. So that means you have a totally renewable heating technology, and we will help us to get rid of the 2.2 tons of carbon emissions from our house.
Yes, that makes a lot of sense and it sounds amazing. And it's nice that it's not just fiction, it's real, this is something that's very, very, very realistic and realizable. And the other question I wanted to ask is, what are the potential drawbacks or challenges associated with using heat pumps? And because, it sounds so good, are there any things that maybe are drawbacks or challenges that you'd like to share?
Yeah, I wouldn't say drawbacks, I would say challenges. And these challenges are obviously can be technical or non-technical. Yes. Let's start with the non-technical side first. So obviously one of the challenges we are facing is, for example, the heat pump installation in the UK is quite low compared with other countries. On average, we only have 1.5 out of 1,000 households are using heat pumps. And this is much, much lower than the average installations in the UK or in the EU. And so this is one of the challenges we are facing. So but the question you just asked is why? So why the uptake or the installation of heat pumps are not very high at the moment? And one of the reasons is about the cost. So if we take a heat pump as an example, an air source heat pump as an example, so the cost for a unit, for a system, is about 3,000 to 5,000 pounds. And that is the price for the device itself. But then you need the installation.
Yes.
And like you install a boiler, you need engineers come in to install your heat pumps. And the installation is quite expensive at the moment, because normally this will require you to retrofit in your central heating system a little bit.
Yes.
And for example, we need to have a much bigger radiators, and we need to insulate our houses, and so on and so forth. So that will add the cost up. So roughly, adding the installation costs and with the product cost, it will be 3 to 5 times like the cost we need to install a new gas boiler. So that is quite substantial, right?
Yes.
Yeah, for most of our kind of households.
Indeed.
Yeah, and so this is obviously is a quite challenging situation. But the good news is the government knows that.
I was going to ask you that.
Yeah. so let's say in May, and the UK government actually launched a new policy called boiler upgrade scheme.
Wow,
so basically,
okay.
They provide about £5,000 to support our homes to install heat pumps, and that is cash, £5,000 for air source heat pump, and then £6,000 for ground source heat pump. So this is for people living in England and Wales, and for Scotland we have a similar scheme called the Home Energy Scotland Grant.
I see.
Yeah, that's quite similar, but actually it's more kind of the support is even higher. So you can probably apply for up to £7,500 to install a heat pump.
Wow.
Yeah, so that is actually substantial support for us to switch from a gas boiler to heat pumps. Yeah. So this obviously their supports there, but also I think there's a wider discussion and debate how we're going to develop new financial tools and business models, and to help us to install heat pumps, because we have to do this, and the sooner the better for us to help to reach the net zero. And so these are the kind of non-technical challenges we're facing. But on the technical side, and I would say there are also kind of different kind of challenges for, because heat pump is a wide range of products if you looked at it, right? But then you want to install heat pumps in a particular home. Each home have different situations. And so, for example, in Scotland and in some areas, and the temperature is lower than the temperature in south of the country, right? And so all these conditions need to be considered when we install heat pumps. It's not like installing a gas boiler, as there will be more considerations. And one of the things from the scientific or research perspective is when the temperature drops, for example, like today, -10.
Yes.
So then the performance of heat pumps will drop substantially as well, because when you operate your heat pump, the smaller the temperature difference between your source, that is air, for example, and your hot water.
Yes.
The smaller the temperature difference, the better the energy performance.
Interesting.
Yeah, if the temperature outside is too low, then the performance will drop as well. So if we think we have relatively a low temperature in winter, and so there are also challenges will come in as well, like you have frosting, building up on your outdoor unit. So these things can be addressed through innovations, through research, and that's exactly what my research team is working on.
Fantastic. That's really great. And what I really love about your approach to explaining this to us is the amount of facts and figures that you're giving us. It's really, really helpful, really, really educational and informative. So yeah, that's great. We could talk about this all day, couldn't we? There's so much to cover, but I think at this point we'll take another music break, and when we come back we'll try to wrap up the show. So we're going to listen to a beat entitled Diaspora. So I made this beat. When I was making it, I was thinking about what maybe a machine would sound like. Use your imagination and imagine that this is how your heat pump sounds. Hopefully it doesn't sound that way. Maybe that means something's wrong. But yes, enjoy this track. It's an amapiano track entitled Diaspora, and we'll be right back. Well, great. This is the Science Show on Jambo Radio Scotland with Dr Dada, and we're broadcasting live from the city of Glasgow. I would like to take this opportunity to shout out to our sponsor, IOP Scotland, for sponsoring this episode of the show. And of course, remember you can listen to us on DAB, and you can also watch us live and listen live at jamboradio.co.uk. And episodes are also uploaded to our YouTube channel, Jambo Radio Scotland. Great. So now we're back, and let's take up our discussion once again with Professor Yu. And just a couple of more questions to ask on this topic then. So, heat pumps. Of course, you had an invention of a new kind of heat pumps. And would you like to tell us about that?
Yeah, I wouldn't say it's a new kind of heat pumps. I would say it's more like an improved version of the existing heat pump technologies.
Good.
So,
okay.
Yeah. So when we look at these heat pumps, and particularly air source heat pumps, you are basically extracting heat from air. So there are a few, technique areas you can look at. For example, like in a very cold day. So if you try to extract heat from air, so what will happen is you will start to have a frost building up and on the outdoor unit. So this is like a little bit like you know in a cold morning you come out and you see the frost of your screen shield on your car. So it's the same mechanism. So when the air temperature is too low and the humidity level is high, you got this problem. And for air source heat pump, and this is not very good not good because once this ice start to build up, it will reduce the performance of the system. It will reduce the ability to absorb heat from air. And one of the things is we need to regularly to turn down the system and then to defrost it, and that is the current practice. And I was thinking, can we find a better energy efficient way actually to remove the ice, to do the defrosting? And then we say, okay, we need to find some energy in the system or somewhere to help us to defrost, to melt the ice. And then when we look at the system, actually, and I found somewhere there is actually heat there, we didn't use it. And So we then say, okay, why don't we use this heat, gather it, and then use this heat for defrosting and for the system operation. So then we actually come up with a new design and a flexible heat pump design. So what happens is, so when we have, we extract the working fluid as a refrigerant from the outdoor unit, and we compress it to high temperature and high pressure, and then send it to the indoor unit, and we call it condenser, to transfer heat to our central heating system. After that process, the liquid working fluid is still very hot, but we don't have another means to use this heat. So why don't we find a way to gather this heat and then use it for later operation? Yeah. So that's what I did. So we actually introduced a heat storage to a standard heat pump system, what we are using at the moment, and then we recover this amount of heat which hasn't been used now, and then we regularly put this heat back to the system to help us to improve this system performance and to help us to defrost our outdoor units. In doing so, you actually improve the system performance and reduce the power consumption. In our calculation, this energy saving can go up to 10%. And so we then actually developed a new generation of heat pumps, and it is flexible, it's more energy efficient, and eventually will be more cost effective for us. And that will eventually help us to encourage more installations. So that is the technology we developed, invented. We call it flexible heat pump.
That's wonderful. That's absolutely wonderful. Yes, deserving of an applause as well. 10% is a lot. That's really, really significant, I would say. So flexible heat pump. You can learn more about that on the profile of Professor Yu at the University of Glasgow, of course, and from his publications as well. Great, that's fantastic. And just one question. So let's go a little bit full sci-fi mode here, if we may. So, what do you think about this? Is this a little bit too crazy as a dream? If you could have a heat pump that operates on a kind of sort of planet-wide scale, so where you can maybe take heat from one country or one continent, one part of the world, and pump that heat into, a colder part of the world, or vice versa, maybe take, cool air and, transfer heat from two different places, climates. Is that something that may be possible, or is this just bonkers?
Yeah, this is a very nice dream, I would say. Yeah, actually, I would say it is theoretically possible, but practically impossible. And actually, I would say, just go back to scale this down. Say, if we have a technology like what we developed, called the flexible heat pump, we actually can achieve your dream in a house. Yes. If you think in our house, we need cooling for like a fridge or freezer, and we need heating for shower, we need heating for central heating, and your fridge, your freezer actually are dumping heat, reject heat to the environment. And if you think in the south of the country, you have a hand conditioning in summer, you actually you extract heat from your house and then you dump it to the environment. But in the meantime, you actually burn gas or use electricity to produce hot water for shower, right?
Yes.
But why don't we actually combine these two processes? We actually take the heat you actually want to dump.
That makes sense, doesn't it?
Yes, and then you upgrade it, increase the temperature to produce hot water. And that is what we try to achieve in the future, say, like you said, in a sci-fi condition. Rather than we have a central heating system in a house, we want to develop a central energy system.
Yes.
That can combine all these energy technologies into one unit. It can produce cooling, it can produce heat. It actually uses the waste heat for our space heating for domestic hot water. So that actually is a small version of your dream.
Yes, and maybe a good place to start.
Yeah.
Well, it's always good to dream, isn't it?
Yes, we need to dream.
Yes, in fact, that brings us to the end pretty much of the show. But before we go, we're going to enjoy a couple of jokes, a couple of science jokes. And I have a few here to do with heat pumps and energy and all that. But I was just wondering, do you have any you'd like to share? Or should I go first?
You go first.
Good. Okay, so one of them says, these are not funny, by the way. It says, one said, why did the gas boiler and heat pump have a heated argument? Because they both wanted to be the one to heat up the house to net zero.
Yeah, that's a good one.
Good. Another one, why did the gas boiler go to therapy? Because it was struggling with its identity as a fossil fuel and couldn't compete with the eco-friendly heat pump. And then another one, why did the gas boiler cry at the funeral? Because it realized that its days were numbered and heat pumps were the future of heating.
Yeah,
so this
that's
is
a good one. That's a good one, yeah.
Good. And maybe one last one. Why did the gas boiler start going to the gym? Because it wanted to bulk up and become more energy efficient, but it realized it couldn't compete with the heat pump's lean, mean, energy-saving machine. So just a few silly jokes there, but interesting because it, kind of brings to mind what we've talked about today. And to round up, let's have a listen to a beat, and we'll try to make a song to this beat. So the beat is entitled Big Dreams. So let's have it, DJ. Thank you. Okay, so I'll attempt to rap to this, okay, or to sing to it. Yeah, so this is about clean energy. Okay, 3, 2, 1. I'm bringing the heat with a new energy. It's clean and it's green, a better way to be. No fumes and no carbon in the air. It's the future of a planet, let's make it clear. Heat pumps reduce carbon emissions, help the planet preserve its condition. Make the shift, let's reduce pollution. We gotta do it now, make it a mission. Clean energy is the best way, it's the priority. Clean energy, it's a better future, make it reality. Clean energy, it's the best way, it's the priority. Clean energy, it's a better future, make it reality. Everybody wants a clean energy. In the winter we need heat energy. Heat pumps is just what we need. It's a better future, reality.
That's wonderful.
Yeah, I need to work on that. I need to make that into a full song. And so please watch out on Spotify and all streaming platforms. Maybe that's going to drop soon. Who knows? Anyway, that brings us to the end on this week's edition of the Science Show with Dr. Dada on Jambo Radio Scotland. Remember, if you want to keep your eye on the advances and developments in science and technology and the impacts these developments are having on daily life, or maybe just to learn one or two things or facts and figures about science-related activity going on here in Scotland, then this is the place to be. So if you have any questions on this show or comments, feel free to email us info@jamboradio.co.uk, and do check our homepage jamboradioscotland.co.uk/ the Science Show for news updates from this show. Thank you once again for listening to this week's edition of the show on Jambo Radio Scotland with Dr. Dada presenting, and the production team. Of course, we have Serena Piotto and Otuekong Umoren, and of course our guest, Professor Zhibin Yu. We're so happy to have you with us today, and next week we hope to have another guest on the show. So tune in same time next week for another exciting edition of the Science Show with Dr. Dada. And until then, we say stay curious.